Howdy folks, it's Mr. Hess back with another geometry lesson. Today's lesson is 2.2 and the title of it is using inductive and deductive reasoning. Okay, so we're going to be trying to reason through things in this module, or the lesson 2 modules, and there's a couple of types of different types of reasoning, one of which is called inductive reasoning. So I've got the definition up here. Inductive reasoning is where we reach a conjecture by observing specific examples or situations. A couple things I wanted you to notice here. First of all, I said conjecture and not conclusion. If you remember right, a conjecture means that it's, you might say, almost like a very well-educated guess, but there is some doubt that I could be wrong. So a conjecture, I think specifically what I said a conjecture was a statement we believe to be true. Okay, but I did put conjecture here because there's a chance we could be wrong. And we're reaching that conjecture then just based off of examples. Okay, so I've drawn some examples of triangles up here, and I want to show you then an example of inductive reasoning. I look at the angles that I have marked in my triangles, and I'm going to see if I can't reach some kind of conjecture here. The first thing I notice on my first triangle is that all my angles are less than 90, so they're all acute. So I might think, oh, hey, all triangles have nothing but acute angles. But when you get to this next one right here, acute, acute, oh, that one right there is obtuse. And even over here, this one's 90 degrees. So I already know that's going to be a false conjecture. So I don't want to go with that one. But when I do look at my specific measurements up here, 68 and 70 and 42, I notice that if I add these up, I get 180 degrees. Let's see what happens here. Let's see if I get the same thing. 9 and 9 is 18, plus 2 is 20, carry the 2, 5, 6, 7, 8. Oh, what do you know? 180, 180. So far it's working. 37, 53, and we know this mark means 90. Okay, if we look at those angles on that triangle, once again, I think you're going to find they add up to 180. So that would be my statement in this case. Now that I've realized, after these 3 examples here, and the more the examples, the better. So the more examples you come up with, that's the more confident you're going to feel in your conjecture. Because sometimes if you only have a few examples, that might be misleading. But the more examples you have, you tend to cover more and more possibilities, and you feel more confident in your conjecture. Okay, so that would be my conjecture on this one, that all triangles have angles that add up to 180. Some other examples of this, just to give you an idea too of inductive reasoning. I did mention once before that I've made the conjecture that tomorrow morning the sun will rise. Okay, that's a conjecture that I'm making that could be false. I could be wrong, but it is based on specific examples. I'm basing it on the last, billion years, where every day, day after day after day, the sun has risen in the morning. So I have plenty of examples that indicate that that's going to happen again tomorrow morning. So I can make that conjecture pretty safely, pretty strong conjecture. Other ones that might be weak, imagine if I was a sheep farmer and if I was limited only to my farm and I didn't get outside of my farm very often, so I didn't get a chance to see the outside world. But within my little farm, maybe every one of my sheep are all white. So I might come up with the conjecture that all sheep are white. Because, my limited examples on my farm indicate that. Well, as you may very well know, there do exist other types of sheep. There's black sheep. I've even been told there's even gray ones. But that would be a counter example then. If you said, well, no, you're wrong on your conjecture. There do exist black sheep. So that would be a counter example that would prove that one wrong. Okay, so inductive reasoning is not perfect, but it is a type of way that we can reach a conjecture by just observing, and seeing a bunch of examples that do that. Now, the other type of reasoning that we're going to learn about in this lesson is what we call deductive reasoning. Not inductive, but deductive. Now, deductive reasoning, we're going to reach a conclusion. Not a conjecture, but conclusion. So this time, instead of having some doubt, like a conjecture might have, a conclusion means we know for a fact we are correct. Okay, and we're going to reach that conclusion based on logic. Okay, so logical reasoning, you got to be able to think for these. You got to think them through. And that logic could be things such as definitions of terms, properties that we've learned, like, for example, in algebra, the addition property says whatever you add to one side, you got to add to the other to keep it, nice and balanced. So those are properties that we might use. Postulates. Remember, postulates are things we know to be true, we just can't prove. And theorems. Okay, theorems are often what we are going to actually be proving. But once you've proven a theorem, now you're welcome to use that theorem to prove other theorems. Okay, but you could use any of those or any other facts, that you might know. Okay, so we're using logic, we're thinking it through based on facts. So let me give you an example. And this is an example which I don't expect you guys to be able to do just yet, but I want to show you an example of a geometric proof here, a geometry proof. So if you see in this picture right here, I've got a picture of a triangle, and I've drawn a line through the top vertex here, and over here I have some given information about this drawing, and in my given information it mentions that this line AB at the top here is, and that symbol means parallel. So that top line here, AB, is parallel to this bottom line, CD. So these are going to run in the same direction, so to speak. And based on that given information, I am stating here that you should be able to prove, it can be done here, you can prove that these angles, 1, 2, and 3 here inside of the triangle add up to 180. Now, if you remember, right, that's the conjecture I just made a little bit ago in our example for inductive reasoning. So this time I'm looking at it from a different approach. This time I'm going to show you that the angles of a triangle do in fact add up to 180, and I'm going to prove to you why it's true. Okay, I'm going to come up with a conclusion this time that they add up to 180, and I know I'm going to be right. All right, so the given statement is really your starting point here, and we're going to create then what's called a two-column proof. Okay, you see how I've split my board into two columns? And when you do it, and a two-column proof, by the way, is the most common type of proof that you're going to see out there. And in a two-column proof, you're putting your statements on one side of the board here, and then my reasons on the other side. Okay, that's what makes proofs difficult, is that you actually have to give a reason for every step you take. So anytime I write a new step here, I'm also going to have to justify why I did that step. All right, so the first step of a proof, though, is very simple. It's very easy. We're just going to start with this given information. So that's what I'm going to write for our first statement. I just have to copy this down and say line AB is parallel to segment CD. And how do I know this? From my reason. Okay, this is a very simple reason too. I knew this was true just because it was given. It was given to me. So for my reason, I simply put that it was given. Okay, every proof should start like that. You always start with the given and just say it was given. So it's the easiest step to write in a proof. You know, if you can't come up with this first step, then you're in trouble, because all you have to do is copy the given and say it's given. Now, until you get good at proofs, you might not be able to figure out where to go from there. I'm going to start to fill out this proof since, I got a little more knowledge about proofs and stuff. I just want to give you an idea of what it's like here when you do a proof and what deductive reasoning would be like. Okay, so if I know those are parallel, eventually, again, this is something you haven't learned yet, but eventually you're going to learn that when you have parallel lines, there's certain angle relationships that occur. And one of those angle relationships is going to state that this angle 4 right here, and let me regather my train of thought here. I'm actually going to state this first. I'm just going to state that angle 4, 2, and 5, if you put those all together, 4, 2, and 5, you see how they make that nice straight line? Okay, so I could say then that since they make that nice straight line, or we call that a straight angle, right? Then by a definition of a straight angle, I already know that this is going to equal 180. So angles 4 plus 2 plus 5 all have to add up to 180. And I'm going to state over here for my reason, I'm just going to put down that straight angles equal 180. It would technically be a definition I'm using. But straight angles equal 180. Okay, now as I was getting ready to say, there is some angle relationships that occur whenever you have parallel lines. And when those parallel lines are cut by another line like this called a transversal, then we create some angle relationships. One of which in this picture is going to be this. See the angle 4, which I'm going to mark with this double there. See that angle 4? And this angle 1. Those two will match. They will be what we call congruent. So angle 4 is congruent to angle 1. And by the same reasoning, not only does 4 match 1, but over here on this side, the 3 down here, I'm going to mark it with just a single arc, is going to match the 5 up here that I'll mark with a single arc. So 3 and 5 are also congruent. Now I'm going to list them both in this same step because they both have the same reason. Okay, the name of that special pair you're going to learn about in the future is what are called alternate interior angles. So over here for my reason, I'm going to mention that I knew that alternate interior angles are congruent, and I probably should say when lines are parallel, because the lines did have to be parallel for that to work. But alternate interior angles are congruent when lines are parallel. Okay, now, my ultimate goal again was to prove that all 3 of these angles inside of the triangle add up to 180. I did start out with something close to that, instead of 1, 2, and 3 equaling 180, I did start out stating that 4, 2, and 5 equal 180. Those were those three, remember, that made up the straight angle. So at this point, I'm going to do a little bit of manipulating. I'm going to look back at my previous step, and if 4 is congruent to 1, do you see where I had a 4 up here? I'm going to take that 4 and I'm going to replace it with the angle 1. So I'm going to be putting an angle 1 in there for 4. And on the same idea, the same note, see that angle 5 over here? 5 was congruent to 3. So I'm essentially going to take the 5 out and I'm going to put an angle 3 in for it. So now I would have this following statement. I would have angle 1 plus 2 plus 3 equals 180. Okay, what I did was a type of property, by the way. We have all kinds of properties of equality, and one of them says if these are equal, then that means that you could always take one of these out and put the other in. In sports, when you do that, when somebody goes out and another person goes in, it's called a substitution, and that's what we're doing here as well. So this is called the substitution property. Okay, so there you have it. There's an example, and I'm done, by the way. Did you see that? 1 plus 2 plus 3 equals 180. 1 plus 2 plus 3 equals 180. So I got there, see? But do you see how one thing kind of led to another? You know, the statement number 2, I just kind of looked at the picture and I saw the straight angle. I knew they added up to 180. But then I used the idea of the parallel lines to help me state that I had congruent angles. So I used that parallel part up here to come up with this step 3. And then the step 3, the fact that those were congruent, I used those to plug into step 2 to create step 4. So you see how everything's kind of relying on each other. Proofs are a lot like if you've ever seen where they set up all those dominoes, and then as you knock one over, you know, one hits the next, and you just have domino after domino knocking each other down. Okay, it's a lot like that idea where previous steps will help us lead to new ones as well. You might even say it's like one of those, I think they're called a Rube Goldberg experiments, where people set up fancy contraptions, you know, like you might have a toaster oven where you push down on the toaster oven, and then when it pops up, it pulls on a string, and the string then releases a ball bearing, and the ball bearing then goes rolling around, and it drops and hits a button that turns on maybe a fan, and then the fan turns on, and it blows the sailboat that moves along, you know, where it's that fancy kind of contraption, you know, where one thing triggers another. Okay, that's called a Rube Goldberg, I think, experiment. But proofs are like that, where previous steps will lead to future steps as well. Okay, again, this is a geometric proof that's a little too elaborate for you right now, but we are going to be doing some algebraic proofs yet in this section, and those are ones that are easy enough that I do expect you to be able to do those. Okay, just to get a little practice, I want to take a look out of your textbook. This is on page 48 in your textbook, but they have this example of Rebecca, it says here, is shopping for a new phone, and so she's looking through all the reviews that people wrote. So I want to take a look at each of these reviews and determine if these are inductive or deductive reasoning on each of these. So if you look at our first review there, this is a great phone. I have 3 of these phones, and each one works amazingly. Okay, so when I read through that, I notice that the person already has 3 phones, so they're basing their opinion of this on those examples. So that first one right there, I would say, is inductive reasoning because we're basing it on examples. Okay, the next one, this phone doesn't stay charged as long as other phones. It has smaller battery according to the specifications. I wouldn't buy this phone. Okay, now this is an example that I would say would be considered deductive reasoning. Because remember that deductive reasoning is where you reach a conclusion based on facts. And it even mentioned in here, it has a smaller battery according to the specifications. So they've already looked at the facts and they know that this phone doesn't stay charged long then because of it. The next one there, I would not recommend this phone. I know 4 people that bought the phone and they each had troubles. Okay, so this person again mentioned 4 previous people that are examples, and they all came out the same and they all had trouble. So they're basing their conjecture here on those examples. So this would be inductive reasoning, where we're basing it on examples, not necessarily facts. Juan says the phone is perfect size to fit into a pants pocket easily. I checked the size before I bought it. I have told all my friends to buy this phone. Okay, this example I would say is deductive reasoning because he did check the size. You know, he knows for a fact, he measured it, that it does fit into his pocket easily. So his statement is based on fact, not just opinions or examples. And finally, this last one, Frankie says, everyone in my book club has this phone, and they all say it's the best phone they have ever used. Okay, so again, he's basing this one on a bunch of examples. You know, everyone in his book club apparently had the phone. So however big his book club is, he's got that many examples. They all said it's the best phone, so he's saying, okay, it must be the best phone if everybody's saying it is. But again, that's based on examples, so that's inductive reasoning on that one. Okay, so if you see it based on a bunch of examples, that's inductive. If you see it based on some facts, that's deductive. Okay, now I'm here on page 49, and there is in your book some properties of equality listed here, but I don't like how short this list is. In algebra, we use all kinds of properties of equality in order to do our algebra work. And these are only 4 of a much larger list. And these are just the basic ones that you usually run into when you're doing algebra. Because let's face it, at different times you have to add, subtract, multiply, and divide. Okay, and all 4 of these listed here in your textbook all really say the same thing. They just say, like this one says, whatever you add to one side, you have to add to the other. See how they put a plus C on both sides? Okay, subtraction property says whatever you subtract from one side, you got to subtract from the other. So there's a minus C, a minus C. You know, multiplication property, they multiply both sides by C. Division, they divided both sides by C. Okay, but there are more properties than this. So I'm going to show you in another textbook I have here a little longer list of properties of equality. Okay, so I still have those ones I mentioned earlier. We still have the addition and subtraction, the multiplication and division. You know, in this book they grouped addition and subtraction together because they're just opposites of one another. Multiply and divide are opposites, so they put those together. Okay, but they also show you quite a few other ones that you may want to pause this video and copy these properties down so that you'll have them to use on your test. Okay, but I'm going to go over each one of these one by one as well on my board. All right, well, up on the board here then is a list of all those properties that I was just mentioning and some examples of each then. The reflexive property, and you should recognize, by the way, the names of these properties from when you learned algebra. Excuse me, when you learned algebra. So the reflexive property gets its name from the idea that when you look in the mirror, you see your reflection. Okay, so they're identical to each other. So you'll notice in the reflexive property, and I give examples here, by the way, both segments and angles, since in geometry we work often with both. But the reflexive property for segments would say something like this: segment PQ is equal to itself. Okay, over here for angles, angle A is equal to itself. Okay, so whenever you say anything is equal to itself, you're using the reflexive property. Okay, you might think that's not very useful, but believe it or not, that does come into play in geometry, especially when we get into proofs more in depth, and when we're proving triangles congruent, if they share a side, we say by the reflexive property, that side has to be equal to itself, for example. The symmetric property. The symmetric property often gets confused with the reflexive property. It's a little bit different, and it gets its name symmetric from the idea of symmetry. Like my body has symmetry. I've got an arm on each side. You know, I've got an eye on each side. I got an ear on each side. Okay, I have symmetry. So both halves of my body are equal. So if I face this way, you know, that'll be the same thing as saying that if I were to flip around, I'd still be equal on both sides. You know, so my arms were equal here, and even if I flip it around, my arms are still equal on this side. Okay, so here's some examples of segments and angle ones. If I already knew that PQ equals RS, since the two of these are equal, according to the symmetric property, I can flip it around, and instead of leading with PQ, I put it at the end. Instead of ending with RS, I put it at the beginning. So I'm just switching around both sides of the equation since they're equal. Same here. If A equals B, then B equals A on the angles. Okay, so again, try not to confuse that reflexive. Reflexive, they literally match, nothing different. Whereas symmetric, they're just equal, so they can be written forwards or backwards. All right, the next couple that are up here, again, are kind of closely related. They often get confused with one another. The first one I want to cover here is the transitive property. Transitive. Now, if you think of other words with the same prefix, you know, like a transit system, it is a system then that you travel along. You know, a transit system might be like a subway, or you know, airplanes are a transit system, or railroads or cars. Okay, they're all ways to transport yourself from place to place. Okay, so the transitive property, again, is going to follow that same concept, that idea that you're traveling along a route. Okay, and the transitive property, I like to say, is again a lot like that idea that I talked about earlier with proofs of the idea of dominoes, where one idea knocks down the next. So this leads to this, which then leads to the next, which then leads to the next. You know, it's a chain of events. Okay, a chain of events. So think of the transitive property like that. In order for the transitive property to work, then there has to be a middleman that connects the ideas. So if you look at my first example with the segments, I've got if PQ equals RS, where RS is going to serve as my middleman, because look at the very next statement. I know now that RS is equal to TW. So because they had that RS in common, and because our middleman is literally in the middle here, connecting the ideas, then what I can essentially do is I can forget the middleman, cancel him out, and now I could just say PQ would be equal to TW. See that? Since PQ is equal to RS, and RS in turn was equal to TW, I can eliminate the middle and just say PQ equals TW. Same thing's going on over here for the angles. I have angle A is equal to angle B, and angle B is equal to angle C. So B again is my middleman connecting the ideas. So if A equals B and B equals C, I can eliminate the middleman, the B's, and just say A would have to equal C. A equals C. Okay, so that transitive property again has to have like a domino effect, and there has to be a middleman connecting them to keep that chain going. Where the one left off, the other one begins. Where the one left off, the other one begins. All right, substitution. Substitution property then is often confused with transitive. Here's the difference though. Transitive is limited to having that idea that wherever you left off, the next one has to begin to keep the chain going. A substitution is a little more open to other possibilities here, because in a substitution, we're just saying basically, as long as two things are equal, I can pull the one out and put the other in. Okay, as simple as that. If two things are equal, I can pull the one out and put the other in its place, as long as they're equal. Okay, so see in this statement, I've got if I knew that segment PQ plus segment RS equals 5, and if I knew that RS equals TW. Okay, that's the important part. Here's my statement. I got two things equal. So that means that anywhere up above here now, anywhere where I see any RS's, I can replace them with TW's. So that's what we're doing here. I'm going to take this TW that I know is equal to RS, and I'm going to plug it into this RS right here. So TW goes in there, and then if I put a TW in there, you see you're going to have PQ plus TW equals 5. Okay, so after plugging that TQ in, right there it is in my last statement, see? Same thing over here. For angles, I've got angle A plus angle B equals 180. And if I know that angle B is 30, then I could take this 30, I could plug it in up here for angle B, since they're equal. So I'm plugging it in there to get this 30 right there in that statement. So now it becomes angle A plus 30 equals 180. Okay? So hopefully you see the difference there between that and transitive. You know, here I'm just plugging in. Okay, up here for transitive, I'm essentially just eliminating the middleman. Okay, some would argue though, some people would look at it and go, well, if RS equals TW, couldn't I plug the TW in right there for the RS and get that last statement? Yeah, that's why oftentimes people confuse transitive with substitution. But when it's set up nicely like this, where the middleman's already, you know, it's the end of this statement and the beginning of the next one, it flows so nicely that you don't even have to consider the idea of substituting, because it flows so nicely, we could just use the transitive. All right, now the next property was the distributive property. If you've done any algebra, then you know what the distributive property is. Here's an example for segments. If 3 times the quantity PQ plus 2 equals 18. Okay, if you have parentheses like this, you have an unknown value inside the parentheses, then one of the only ways to get rid of the parentheses is to distribute. To take this 3 on the outside and you multiply it times each term inside. So 3 times PQ will give you 3PQ. 3 times the 2 is the 6. So there's our distribution. After we're done using that property, we end up with 3PQ plus 6 equals 18. Same thing over here. We take the 4. We're going to distribute it times each term in the parentheses there. So 4 times the measure of angle A is just, well, 4 times the measure of angle A. Minus 4 times 5 would be 20. Equals 38. So I've distributed the 4. Okay, now don't forget the other 4 properties that were in your textbook. These were the only 4 they listed, though, in there. They didn't give you any of these. Okay, but those 4 are very simple ideas. These 4, in fact, fall under what people often call the golden rule in algebra. Whatever you do to one side, you got to do the other. So I gave an example of, for example, the addition property right here. Suppose we already knew that P cubed minus RS equals TW. And let's say I wanted to get this P cubed by itself. So I would get rid of this RS by doing the opposite. Instead of subtracting an RS, I would add an RS. But whatever I do to one side, I've got to do to the other. So I'd have to add an RS not only on this side, but also on the other side of the equation. Now over here it cancels, so that's why the PQ will be by itself. But now on that side, do you see I have this? I have TW plus RS. TW plus RS. Okay, the name, by the way, comes from what you did to both sides. I added to both sides. That's why it's the addition property. Do not name it by what you already see there. Like here, I already saw a minus sign. Okay, but to get rid of it, I had to do the opposite. I had to add. So that's why it's addition property being used, not subtraction. I'm getting rid of the subtraction by adding. Okay, over here, I gave an example of a division property problem. Since addition and subtraction are very closely related, I figured I'd show you one of these two then, multiplication or division over here. So I started out with a problem like this where I know that 3 times the measure of angle A equals 81. I want to get the measure of angle A by itself. So I get rid of the 3 that's currently being multiplied by, you guessed it, dividing. You do the opposite, you divide. And whatever I do to one side, I have to do the other. So over here, the whole point of dividing was so that these cancel. I wanted to get the A by itself. And then over here, 81 divided by 3 is 27. Again, it gets the name division property because that's the action I took. I divided by 3 on both sides to get this answer. Again, it does not get the name from what's already there. Already there, they're multiplying, but to get rid of it, I had to divide. So it's the division property. It's what I did. It's whatever action I took that I did to both sides. And remember, whatever you do to one side, you have to do the other on all these. All right, so that's our properties of equality. And I wanted to bring those up because we're going to use all of these properties of equality in order to do an algebra proof. Okay, so that's what I'm going to show you next here. All right, so up here is a algebra proof problem we're going to do. They will come up with some kind of algebra statement. You know, on this one, we have if 3 times the quantity x minus 5 equals x plus 1, then x should equal 8. Okay, so they already have the solution, as you can see, and this is the original starting problem. What you're going to have to do if you're doing an algebra proof then is you're going to have to show each and every step that you take to get from the original equation down to this answer. Now, every proof, as I have mentioned, has a given statement and a proof statement. Okay, think of the given statement as where you're starting at. Okay, the proof statement is where we want to end up at. Okay, so we're starting with this if part. If we already know that 3 times the quantity x minus 5 equals x plus 1, and we're trying to prove this last part. We're trying to show that x then is in fact 8. Okay, so anytime you see a proof and you have to write your own, if you have an if-then statement, okay, you're going to find that your if part of your if-then statement is your given, and the then part is the proof part. Or in other words, the hypothesis. Remember we talked about hypothesis and conclusion. So the hypothesis is the given, the conclusion is what you're trying to prove, the then part. Alright, so the first step of every proof, again, is very easy. If you miss the first step on any of your proofs, you should be ashamed, because all you have to do is simply copy this first given statement. So I'm just going to copy this again. And the reason I know this is true is because it was given. Okay, it was my if part. I'm already saying, well, if this is true, I'm going to give you this information. Okay, so that's given. That's all you have to put for the reason. So the real work of a proof then starts in at step 2 here. Okay, and we're doing algebra here. So when I was teaching you my crash course of algebra, you remember I said, well, take a look at this equation, and you may notice that it has more than one x value, and they're on opposite sides, like a sheriff and a, yep, you guessed it, bandit. That's a sheriff-bandit situation. Okay, and normally you would take on that sheriff-bandit situation, but I do notice one other thing. When I look at my problem, I see I have parentheses. And remember, when you're doing algebra, remember it was that PEMDAS only backwards. So it was PSADME. So you do have to take care of those parentheses first. Okay, so before I take care of these x's, let's get rid of the parentheses. Okay, you know that in order to get rid of those parentheses, there's only one thing I could do here. I have to take the 3 that was here, and I have to distribute it. I have to multiply it times each of these. Okay, so I end up with 3 times x is 3x. 3 times negative 5 is 15. Negative 15. And then I'm going to just rewrite that part over there, x plus 1. Okay, since I distributed, I have to explain over here what I did. Okay, I was making use then, of course, of the distributive property. That's one of our properties, the distributive property. Okay, you are welcome to abbreviate on some of this stuff if you find that easier. Just make sure you don't shorten your abbreviations too much. There are 2 properties that both begin with sub. One is subtraction and the other is substitution. So be careful. If you want a subtraction, you should at least abbreviate out to 4 letters, SUBT. Or if you want substitution, again, go 4 letters, SUBS. Okay, because if you just put sub, I don't know if you mean subtraction or substitution. Anyways, I just want to bring that up. Just happened to think of that. I'm going to now look at step 3. Now, in step 3, I'll finally be able to address that issue I was just pointing out a little bit ago. I've got an x here. I got an x here as well. There's my equal sign, so they're on opposite sides, like a sheriff and a bandit. And in a sheriff-bandit situation, what I've taught you to do is to get rid of the weaker one. So I've got a 3x, I've got an x, x being the weaker one. I'm going to subtract that x to get rid of it. I'm doing the opposite, right? This x is being added, so I'm going to subtract it. Whatever you do to one side, you have to do to the other as well. So I'm going to subtract that x on the other side as well. That means that's going to leave me with 2x minus 15. These cancel, so equals 1. Again, I got to explain what I did. And from both sides, you can see I subtracted that x. So I'm using the, okay, here's where I could do that abbreviation I mentioned earlier. If you are going to abbreviate it, remember, for subtraction, you need to put at least the t on there as well. SUBT. So subtraction property. Okay, we're doing this order of operations backwards, and we've been looking for adding and subtracting to do here. And so far we subtracted the x. I could keep adding or subtracting though. You see, if I want to get this x by itself, I need to get rid of the 2 and the 15. And one of those I can get rid of by still adding or subtracting. That minus 15 I can get rid of by adding, right? Do the opposite. If they subtract, you add. Whatever you do to one side, you got to do the other. So I'm going to add 15 to both sides here. And I end up with 2x. This cancels. So 2x equals 16. And to get to that answer that I have so far, remember again, I had to add to both sides. So over here, I'm simply going to say that I'm using the addition property. The add property, addition. I'm almost there. I've almost got x by itself. Notice I still have a 2 in front of the x. I can get rid of that 2 though by dividing by 2. So in my fifth and final step, I'm now just going to have x equals 8. I got to the final statement. Okay, now be careful though. Even though the first statement is always the given for your reason, you do not, when you get to this down here, you do not put that your reason was proof. Okay, that's never going to be a reason in any proof. Okay, the last statement, up here, this was our goal when I said prove that x equals 8. Prove is never a reason that you use though. If you look, we divided by 2 on both sides to get to this. So if we divided on both sides, we made use of the division property. Okay, so there you have it. An algebra problem that we solved in a total of 5 steps. Okay, the first step always given. Then we distributed. We subtracted the x from both sides. Subtract. We added the 15 on both sides. Add. We divided by 2 on both sides. Division to get that. One last thing before I end my video here, but that'll help you then with any of the algebra proofs that I'm going to have you do on the homework. The last thing I just want to mention, and this is just kind of an overview of proofs and how geometry works really. I want you really to just keep in mind that algebra proofs are easy. On algebra proofs, and these are reasons that you have to worry about. When you do a proof, you got statements and reasons. Well, on an algebra proof, the only reasons you ever end up using are all those properties. Okay, all that big list of properties I gave you, distributive, substitution, addition, multiplication, division, all that stuff. Okay, now, and these are possible reasons that you would see on a proof. For algebra, it's just the properties. In geometry, when we do a geometric proof, which I gave you a sneak peek of earlier when I showed you how we prove that a triangle has angles that add up to 180, there it gets even more complicated because like the algebra proof, all of these properties still apply. So you still have all those properties. But the list grows much bigger on all the different possible reasons you might use in a geometric proof. You won't be limited to just properties. You might also make use of definitions. You might use postulates that we talk about. Remember, postulates are true statements we can't prove, but we know they're true. You'll even have theorems, and I know, like in geometry, that's the whole point. Theorems are statements we can prove, and so the proof that you might be doing might be a proof of a theorem, but that doesn't mean you can't use other theorems that we already have proven in your theorem proof. Okay, so what I'm trying to say is that you could think of geometry kind of like a building. And when you go to build any kind of building, the first thing you want to do is have a nice, strong foundation. Okay, you wouldn't want to build a big skyscraper in the middle of a swamp where it would sink. Okay, you want to have a good foundation. You know, you want to be on bedrock, as they say. So the foundation of our geometry building is made up of mostly the postulates. After all, we can't prove them. So they are ideas that we know are true. We just accept them as true. But believe it or not, then they are down here. Postulates make up a lot of the foundation. But in addition to that, there are also the properties and definitions that we're using. Okay, those you could say are down here in this foundation as well. So we got the properties as well and some definitions. Okay, but that's what we start with. You know, that's like our beginnings, our basic building blocks. And then by putting those postulates, properties, and definitions together, we should be able to create our first theorem. So our very first theorem that we make up would be like the first story of our house. You know, we're building on that foundation. So that theorem, as well as any other early on basic theorems, would be like our first floor of our house. Okay, but then we might come up with even more complicated theorems that are built on the theorems that we just learned earlier. You know, so it'd be like a second story to our building. So we could have even more theorems that are based on these theorems, which were based on the postulates and the properties and the definitions. And so on. It keeps working, where it keeps stacking up. It's almost like that game of Jenga, where, you know, you've got all these blocks stacked up in a big tall tower. So we've got theorems after theorems after theorems that we keep learning. And they're always based on previous theorems that we had already learned. Okay? And, you know, eventually this just gets capped off here, and then there's our house of geometry, so to speak. Okay, now, of course, if any of these postulates or early on theorems down here that are the basis of these other theorems, if any of those were proven to be false, then our whole building would come collapsing down. You know, if our postulates were bad, they wouldn't be able to hold up this theorem, which in turn was the basis of that theorem, which in turn was, you know, so on and so on. So if you take out the very bottom of it, the whole thing's going to come down. So hopefully we never find any of our postulates or properties or definitions to be incorrect, because that could be devastating. Okay, so the geometric proofs are going to be harder because they have a lot more reasons than just the properties that we covered. But for tonight's homework, I'm not going to give you anything harder than an algebra proof. So those properties are all you're going to have to worry about, at least for tonight. Alrighty, I think I've taught you enough. I'm going to cut you loose and let you work on your homework.